this it? Is this a crowd? Is this a quorum?
Not quite.
Not quite? How many more?
A lot more.
It's been just about double, I think.
Pretty, once everyone's here, it's full.
Yeah, usually almost
It really is full when everyone's here.
But everyone's not coming today.
Wow.
That's what you're trying to, not hurt my feelings. Right?
I mean,
Okay,
you're
that's
not
cool.
exactly an A-lister now.
We can make this work. We can make this work. Is this the light from the front, right? Wrong one. Not that one. There we go. Because we're gonna go. Is that okay with you?
Yes.
Just to make sure you're in the right place, this is AFE prep for mechanical engineers in the future, yes?
Yeah.
Okay.
Sounds right, bro.
So this is the solid mechanics review, or how fast can we review an entire quarter's topic in 120 minutes?
Welcome everyone to the Utica Speedway 22nd Annual Formula E Enduro 120. Looks like the lights are up, and we are racing to get this review done in 120 minutes.
Okay, it's way too hot in here. Not very professional. Don't feel like an engineer yet. Although, you know, on the Formula One racing, is anyone following it, by the way? Finally, got someone in there. It's got nothing to do with the racers and everything to do with the constructors, doesn't it?
Yeah.
Who are you rooting for?
Well, Max Verstappen.
That's a racer, that's not a constructor.
Well, Red Bull. I read behind it.
Yes. Red Bull and, what's it, Toro Rosso
Yeah.
and their team. Good group of folks. If you don't get into F1 racing as a mechanical engineer, I feel sad for you, because there's so much you can catch on that one, especially with the engines and the technology that are going into it. It's a whole lot of fun in that regard. And it does mean that we need to go very quickly in your mechanics review in order to get you back up to speed. You have anywhere from 9 to 14 questions that you had to nail out. You got 3 to 4 minutes to nail every single one of them. These are the topics that you're going to be focusing on collectively. Things like moment diagrams, Moore's circle, axial loading, bending, torsion, shear, a little bit of temperature change that's in there, deformations, column buckling, and statistically indeterminate systems. The nice thing about this is they don't really hit you too hard on that one. It takes a little too long to do those because it takes a little bit more than 3 to 4 minutes to calculate those out. That's the big picture. We're going to cover all of those topics in a very quick review. And as I already just said, 120 minutes to do that in no time at all. You ready to go? Let's go. All right. This should be some flashbacks. Keep up with me here. Tensile tests are the basic mechanism we use to identify or focus in on things like Hooke's law and so forth. This is from a mechanical standpoint, sort of the premise of the stress and strain. Classic formula you're going to use over and over in the quick questions are things like this, such that the stress is a force per unit area, and whether it's P or F or whatever the variable happens to be, it's some sort of force for a given area. Strain, obviously, is a change in length. Original length over the new length minus the original length over the original length. And a comparison to the stress strain becomes the diagrams that we do in a stress strain diagram. You're going to see problems that use that right off the bat, and you're going to see problems that ask you for percent elongation. Those are the two formulas you need. Quick review, what's going on in this diagram, by the way? Explain it. 30 seconds, go.
Stress versus strain.
A little bit more.
There's that SY, the Young modulus.
Okay, what's happening right here?
That's the elastic deformation.
Good, what's happening right here? Okay, plastic deformation, we're making a transition here. I have a yield point at which the plastic deformation occurs. From this point on, I'm going up to the ultimate tensile strength where it fails, or the ultimate overall strength, and then the failure point over here on the other side. Mechanics of material deals with everything on this side over here. Okay, we're talking about bending things and having them come back, compressing things and having them come back. We're not dealing with the plastic deformation stuff. Don't forget that line for the yield point was defined by a 2% offset. Problems are going to be focused also on this. What's the big E? Or another name for it, Young's modulus.
Modulus of elasticity.
Modulus elasticity. The reason I focus on that one is it really focuses on where in the diagram that applies to. And we're talking about things that go back. After the crystalline structure stretches, it comes back to its original form. That's what we just talked about there. The yield points, that's where the bonds are being strained. We get plastic deformation, not so good, a lot of work hardening, straighten hardening, and that's where your product no longer comes back to its original shape. Like I said, mechanics really focuses on the other stuff. We like to simplify things as engineers. So instead of using the regular or the theoretical strain in there, we simply talk it engineering strain. And why do we talk about engineering strain versus true strain? Or stresses from that standpoint?
Just the cross section's actually changing,
And
it's
that-
being elongated.
That's the key to it. Some of the problems will focus on that. We'll make sure you read the problem and make sure they're asking about the engineering stress as opposed to the true stress. Because when you do that, you're taking into account the change in the area. But as engineers, we don't take into account we estimate, we don't take into account the change in the cross-sectional area. We use our more idealized curve. That's what the two curves look like. That's what the strain is also for engineering strain. Same concept, taking into account the fact that the cross-section area changes. When you relate the two, there are ways of giving yourselves, so on the true and engineering strains, there are a way of relating those two. You've got formulas that you're going to be given in your handout overall. So what we're focusing on, like I said, is just this end when we're talking about the mechanics of materials work that you're going to do on the FE exam. What if you squish something? What do we call it? There we go. If you can do the opposite, you can stretch it, get skinnier, you squeeze it, it's gonna get bigger. We gotta keep in mind that that's going to also change things. We could also twist things. So instead of compressing them, we could put torsion on there. And when we twist things, we get shear stresses inside the material. So that's what you see here in the diagram. We're getting those stresses, those circular, in this case, stresses that are occurring. If you look at a little unit section, which we will in a second, those are the ones that go back and forth rather than the plane stresses that are in the motion or the axis of the force that's on there. What's interesting is we had that great big old E for the modulus elasticity. We've got a great big old G for shear stresses as well. And then when you're doing the torsion formulas right here are associated with how much torque you're putting on there to get your maximum shear stress. You can see our modulus of rigidity, which is that big G, I think it's on right there. Big G, which is the modulus of rigidity instead of the modulus of elasticity, and its ability to handle those sort of torsion forces you're putting on there. These formulas, again, are given to you on your cheat sheet. You just need to remember when you need to apply them. And there's also a relationship down here for the torsional yield and the ultimate strength. So, really the basics of all mechanics is the sum of the forces, sum of the moments. It's the massive equilibrium equations. So one of the things in this section you'll definitely do are the free body diagrams. So you have to be good at those. You need to knock those out. That can't be something you hesitate on. And if you can do them and do them quickly, it'll answer most of the questions, meaning it'll set you up for success in the questions that they're asking. So the question might be a little more comprehensive than just the static diagram, the free body diagram, but you need the free body diagram to get all the moments so you can work out the shear forces, so you can work out the displacement, so you can up. So, gotta get good at free body diagrams, practice them if you haven't done so already. Let's try one. This is a little bit more complex than what's on the exam, but partner up with folks around the room. There's a transmission. That transmission has a couple of shafts in it. We're gonna rotate the shafts, but we're not gonna worry about the rotation here at this particular moment. We're very worried, more worried about what we're doing as far as the sum of the moments and the sum of the forces that are in there. You're gonna draw a free body diagram of this particular box. And I'm trying to get you to identify the different pieces. Break off with some partners there. You got 10 minutes. Remember, you only have 3 to 4 minutes on the exam. I'm giving you 10 minutes maximum just to see if you can come up with a couple of quick answers. So here's the goal. You've got a shaft. You've got another shaft. You put a torque on one end. You've got a output torsion on the others. So you can see I've got an input torque of 240 foot-pounds. I'm supporting the different ports. I've got gears that have different radii in them that are transmitting the force from one shaft to another. And your goal is to try to ultimately figure out the end state of the free body diagram. So here are some quick assumptions that you're going to need for your solution. That gears 1 and 2 are simple spur gears, and that there's a standard pressure pressure angle of 20 degrees. That's not gonna come into too big a part. I'll show you where that shows up in a second. The bearings are self-aligning, so they're gonna be simply supported. So now all of a sudden your diagram, simply supported. The weight of the members is gonna be negligible, there's no friction. The mounting bolts are the same size and they're the same distance apart, and that the force transmitted between the spur gears is tangential, but the pressure angle we already know about, given a little formula there, figuring that out. So there is the setup again, so you can see what's going on. So you've got some dimensions. Start sketching out a free body diagram, go. You're allowed to work with a neighbor if you want on this one, just trying to get your juices flowing about thinking about free body diagrams.
Well, yeah, the free body diagram for that, which now they're trying to find. I don't even think he gave a letter or anything, they're gonna get there, but I think he just wanted that every time.
Just the forces of the bearings.
Yeah, but I think the bearing that they have. Yeah. They can convert it, so.
They're simple.
I'm not really sure how to do this.
They're spinning, so they definitely want to. But, yeah.
Got about 5 minutes left. Now that part was done to give you a sense of what minutes are like. That was 5 that already expired. On your exam, obviously it's online. You better already have your paperwork ready next to you on the computer, so you're ready to draw, write, sketch. You don't start the exam and then get that stuff out. You already have your computer out, your calculator, so you're ready to go. So you've got to be ready to hit these problems running. You can't be thinking about it and breaking stuff out partway through the question. You can't afford the time.
Actually, I don't know if it's a thrust bearing or not. Go through that little hole.
Doesn't matter. I guess if it's not a thrust bearing.
You
about a minute left, but by the conversations, I'm worried. I'm not gonna let it go any longer, because we're just gonna press on. Too much to talk about, and I don't want you getting frustrated. Let's do the sum of the moments, sum of the forces. There's the box. Simplify the box so you can see the reaction forces on the simply supported ends. So remember, on the super simple problems you're gonna get, most likely on the exam, they're gonna do things like this. They're gonna give you a beam, they're gonna say it's simply supported, and they're gonna do something on load and say do it. There's gonna be fewer like this. These are a little more complex, but the principle is the same. So if they give you context, you need to figure out the reaction forces, which is classic. In order to figure out the reaction forces at these 2 points, you gotta do the classic sum of the moments, sum of the forces. So you've gotta be able to sketch the concept out, you gotta break it out. So you gotta take it out of this concept here, so you can see the requisite pieces here. So here's one shaft, here's the other shaft. This shaft has 2 supports, this shaft has 2 supports on it. You need to sum everything up on one, sum everything up on the other, and you'll notice we've got a relationship force between the two. This is between the 2 gears. That's what gives it a torque on the two items. And the other classic item that tends to be the simplified problem is when I have a force at a certain point for a given distance, then I get a moment out of that. So most of the time you're thinking, oh, this is a 2-dimensional problem. This is a 3-dimensional problem, and you gotta worry about the different dimensions and where you put the forces. In this case, I don't have moments, which are bending. I have torques, which are rotating. So I'm putting beams or axles under torsion, okay? So you gotta kind of work your way through these sorts of things to figure out what it is you're trying to solve and which way you're trying to solve it. Again, this is more complex than what you're gonna get on the exam, but the fundamentals in this are the same thing that the exam's gonna have on it. So just trying to give you, kind of get your brain flowing in the right direction here. If you did this problem out fully, you'd find forces on the shaft, you can find the normal force on the gear, so you can take the gear's pressure angle to work out the forces that are being transmitted. Then you can finish the sum of the forces in the X and Y and Z dimensions, so now you've got all the supporting forces, these are all the reaction forces I should say, and then you can work on the torsions that go on the shafts, because we put an input torsion on one end, we have a resistive torsion on the other, and we're transmitting it through the gears. When you finish that thing off, you come up with moments around the axis and a torque of about 720 foot-pounds. One last note on this one, there were 4 bolts in the plate. I don't know if you remember seeing those. There's 4 bolts in the plate. You could physically figure these out. Way more complex than what's going to be on the exam, but it is a pretty straightforward process of recognizing that they're symmetrical all about these points, and you can do some very quick sum of the forces again and figure out what the 2 reaction forces are on the bolts all the way around. So that would be the resistance forces on all 4 bolts. Okay. Box, box, box. Everybody stand up for a second. This is what's called an FE, not Formula 1, but an FE pit stop. Move around, shake your arms out. Now sit down. On we go. Beams. This is the more classic, some of the forces, some of the moments, and the shears that are in there. Same sort of equations. You just got to do it in 2 dimensions right now and trying to figure out what's going on. Remember, the shear force and the bending moments need to come up to a sum of 0 in the process. All right, so wherever you slice it, if you slice the beam part way through, some of the forces, some of the moments need to net 0 at that point. So be smart. Put your location to figure this out at a smart point. For example, if that were fixed end down here, I'd use that as one of those starting points, because I know that some of the forces, some of the moments at that point need to be 0. And it eliminates one of the complications on the very end by the wall. Another way of doing it is cutting it down by the end. And getting rid of the end of the beam and finding it somewhere other spot down there. Either way, it's all gonna come out the same. You just need to do the same, some of the forces, some of the moments. Conventions, this is classic. This is on your cheat sheet as well. Positive bending makes a smile. Negative bending makes a frown. Don't forget to get your labels correct on these, okay? That's the one spot people tend to get pinched on this, is they kind of screw up their convention. You'll notice positive shear when looking at it on the paper makes a clockwise direction into the paper. Negative shear comes out at you if you're using the right hand rule either way, okay? Meaning, when you look at it, it's backwards, it's counterclockwise. Distributed load, taking some load of formula whatever, putting it across the beam. You need to worry or figure out the force per unit area. You need to change that, you need to work out the different forces, whether it's distributed or at certain points like this, and work out the changes across the beam based off the differences in the displacement across the beam. If you understand this and can get this, then you can create these two diagrams here. What's this one called? Shear force. What's this one called? Good. And what's the relationship, by the way? We will come back to this again. One's a derivative, one's the integral, depending on which direction you're going. Area under the curve, slope of the curve. Okay? That's a super quick way when you're doing these problems, because what they'll do is they'll do two things. They'll either say, pick the right diagram for this load, and you need to go and do some quick math to make sure you get it, or they'll say, draw the diagram and then pick the one that you would have drawn on there. They're the same problem, they just ask them two different ways. The big picture here is they're going to give you graphs that look identical, but the numbers on here will be different, because they're trying to catch to see if you really know what you're looking at on these diagrams. So make sure you recognize what these different things mean on here and why those points, why is it 210 and not just 200? Because what?
It's the reaction force.
Yeah, because this force is measured here. This is where they did the sum of the forces on this, and this is what it is until you get to this point, and then there's a net change of 200 pounds in this direction. So we know there was a 10-pound reaction force just by looking at this diagram. We could have done that math. So don't look at me like you don't know what I'm talking about. Too many slides to go. There's that relationship. There's the shear based off of the differential of the moment diagram, and the second moment over there for the displacement. And so these are those two equations, whether you're going to integrate it one direction or take the derivatives of the other. Some of you are still looking at me like you don't know what I'm talking about. What's the value of the slope here? Just a rough number.
10.
Pardon?
210.
210, and it's a positive number. Value of the slope here. About 10, and it's a positive slope. What's the slope here? Negative something. In this case, it's negative 90. Other way you can look at it, as far as the different areas. If I notice here, there's a steady increase here. Area, when I'm calculating all the area under the curve right here, I need to make something that's going to constantly get bigger and bigger. Area under the curve is increasing but smaller. Area under the curve is definitely decreasing. So you can look at it from either direction, whether it's an integral or derivative. You can also do this in 2 dimensions. They will on occasion ask a couple of these. They're a little bit harder, but they're not that hard. You simply look at it from 2 dimensions instead of just the x, y, put a z in there. Okay? So you got one set of diagrams. So here's a diagram for 1, here's a set of diagrams for 2. Those are 2 different axes looking in 2 different directions. And what do you do with it when you're done?
Take the result.
What?
Pythagorean's theorem.
Yes. Conceptually, what are we doing? We're taking the load force in one plane, we're taking the load forces and displacements and moments in another, and we need to add the 2 of them up. Vectors. So if I had forces and vectors in different directions, I need to look down at the end of this thing and go, now add up all those vectors in order to get the correct load forces and the correct moments that are on the diagram. So you can make it a 2-dimensional by taking these 2 diagrams, these 2 loads, putting them in their 2 planes, and simply making your triangles out of it. New vector right here becomes the final load force in 3 dimensions. Singularity functions. Anybody remember what those are? Because you just looked at them. If there's a step change in any graph, this is an undefined part right here. So I don't have an equation that covers this part. It's called a singularity. And so we've learned over time, and we did it all in the math, to say, I've got a way of dealing with that. And that's where the singularity functions came out. We've got singularity functions that essentially give me the understanding of what the equation is on either side of a point where there's an inflection point on any of those diagrams. And this, if you remember, are some of those. Point load, point change, step change, and an increase. And And we've already determined formulas for this. If you need these, they're gonna be available to you, and on one of the other sheets, your cheat sheets, these functions exist. Not in the mechanics, you need to go use that section to be able to help you out on this one. Here's a classic one. Bending load force diagram. How would you work it out? Based off of this information, you've got the sum of the forces, sum of the moments equations that you're working up here. You're gonna integrate twice to get the load and the shear moment out of this whole thing. You're gonna note a couple of things, that both the load and the moments are zero at this point. I have reaction forces that can be found by taking the sum of the moments and forces. And right here, you'll notice that at V at 0, x slightly larger than 20 inches, we know that if I know reaction force 1 and reaction force 2 added up with those other forces, all need to balance out to 0. I'm just saying the same thing over and over again. Some of the forces, some of the moments is all you're looking at here. And so this slide is doing the math for that one right there, in case you had trouble with it. Stand up. Box, box, box. This is an FE pit stop. Have you ever watched an FE pit stop? Are they slow?
No.
They're almost instantaneous, aren't they? They're kind of like a singularity function. Sit down. Stresses. What's stress, by the way? Simple formula.
Force over area.
Good. A lot of people are going to choke on that. I'm imploring you not to choke on that. They're going to ask you very simple questions to ultimately determine elongation or compression of something, and they give you a force. Don't choke. You already know the area because they gave it to you in the diagram. You got the force over the area, you know what the stress is. So now you can use the stress and use it in the other part of the formula. Don't forget that the shear stress is the one that's tangent to the surface. Normally it's going to be in PSI, but it can be in Newton meters squared. There's a quick relationship to get pascals out of it. There's the elemental stress element. You should be getting some flashbacks here. For some of you, it's bad. For some of you, it's good. That was the stress element that we're talking about. Predominantly, we start talking out with the stress element in 2 dimensions. So you can see the normal force that will be applied on here and the shear forces, but you'll also notice they come in pairs. So I've got a stress on both ends, or I have 2 shear forces that match up to give me that sort of neutral sort of circumstance. This is the 3-dimensional view of that same cube, same shear forces and normal forces on it. You'll notice it comes in 3 dimensions, so they always come in triples overall, but they're always paired up. Components of stress overall include these various items. Agreed?
True.
Oh, wrong slide. Components of stress include these items. 3 mutually orthogonal surfaces. Each surface has a normal and a shear. Each surface has a normal and a shear. Shears are most often resolved into perpendicular components. First subscript indicates the direction. Second subscript indicates the shear stress. So that's only put together on this slide so that you recognize what these little labels mean in case you're asked about a certain configuration for the problem you're given. Don't forget, in most cases, there's a cross shear. Those cross shears are equal. So you'll match these 2 up. They're going to be equal because there's an equilibrium. The part's not moving when we do these problems. It's static. So everything has to balance out and come out to 0. And so they're the pairs that are already put up there. We can transform these stresses in any other direction. This is not something you're going to be asked in the exam. You will be asked something here in just a second about transforming. That's why we bring this up. But you need to be able to do geometry and a little trigonometry and simply say, what if I slice this? What's the stuff on this surface? Or another way of looking at it is, what if I rotate this with the same forces that are on it? What would be the forces on that cube? Here's why you're doing it. What's the mechanism we use that's really quick and easy to graphically determine shear forces and normal forces in a material? More circle. So we're going to do that, but this was the math getting us to the translations from one position to another. So taking the overall stress, breaking up into components and its shears, so normal and shear forces, and recognizing that if I just do a little trigonometry, I can compare, because it's just a bunch of triangles, I can move one to the different surface on that. So those gave me those 3 principal stresses and being able to move them in different particular positions. And this just got brought up associated with the fact that maximum shear stresses are found to be at 45 degrees. When you do this math, they come out to 45 degrees, which kind of goes back to, do you remember the tensile test? And every time we broke it, we always broke at 45 degrees. Because that's where the maximum shear stress was. And that was based off the math I just showed you in those last two slides. Anyhow, this is the process of getting to that particular point. Oh, these are tips hidden in here. There are always three principal stresses. One is 0 for plane stress. Okay, there'll be 3 extreme value shears, and there they are right there. And what we do is we stack them up in their order, both the shear and the normal stresses, or the principal stresses, I should say. And we use all of that knowledge to ultimately take advantage of Moore's circle to put this together. Because he realized that because we're just talking about circles and triangles, you can graphically put all of this down. You don't need to have all the super fancy math if you just want to use Moore's circle. Who remembers Moore's circle can teach us? I got 2 thumbs and 1 wave of a hand in the back, like maybe, give me a chance. I'll help you out, here we go. That's Moore's circle. Yeah. You will be asked on the exam more likely, either given this circle to read the values off of it, or use Moore's circle to quickly get an answer within the 3 minutes. Here's how you do it. You're going to be told something about a unit that has some shear stress in it or some normal stress. So in this case, we've got a normal stress of 80 megapascals in the X direction, nothing in the Y direction, and I have a shear stress shown on here of 50 megapascals. So we're going to use Moore's circle to figure all the different values out. So here's how it goes. Here's the recipe to get you there. Let's get you with me, come on. Make sure we're going to do it right. So, Moore's circle. First we're going to draw the sigma and the tau, the stress and the shear stress and the normal stress. So give yourself an XY axis. Shear normal stress is on X, shear stress is on the Y. Good so far, that was easy. So now, on that X and Z axis, I'm going to locate my 80 megapascals along there, because I'm going to go out here, 10, 20, 30, 40, 50, 60, 70, 80. So there's my 80 megapascal point right there. On the X element, I notice that I have a shear stress of 50. So, and it's in a clockwise direction. See that 50 right there? It's in a clockwise direction as shown on the diagram up here. So I'm going to take that knowledge right there, and I'm going to go up 10, 20, 30, 40, 50. And that point now is my 80, 50 point, right? That constitutes what I know about this side over here. And I need to, oh, I better put that clockwise on there because that's important. Next up, on the corresponding Y face, I look at the Y face, I have no normal stress, kind of makes sense, and I have 50 megapascals in the counterclockwise direction, So on that, knowing what that is, I'm going to locate that point at 0, 50. 10, 20, 30, 40, 50. See where I'm going? Line AB. So connecting these two right here, that becomes my radius of the overall setup of the circle. Well, the diameter when I draw it all the way through here, because I'm going to draw it all the way through like this. But that's going to be my circle that I'm going to be drawing on here. The intersection of the circle with the axes defines both that sigma 1 and sigma 2. Now, in drawing that circle, you have to draw it to scale. Based off of this right here, you get something that looks like this. Perfect circle. Man, that was so good. The intersection there is going to give me my principal stresses. I've got a triangle right here. The legs A, D, and CD that I'm going to show you in a second are 50 and 40 megapascals each. All right, I've got 50 over here. I've got, is that 40? 20, 30, 40, 50, 60, 70, 80. And I can figure out the hypotenuse, which is this section right here, which is ultimately going to be my radius, which is my shear stress. You can see it's that square root of the A squared B squared, 50 squared, 40 squared. Comes out to 64 megapascals. And that intersection of line C from that origin now shows me where my other stresses are. Here's what I'm looking at, by the way. That's the bigger diagram of what we were just drawing. there's my 80, there's my 50, so there's my 50, 80 counterclockwise point. I drew this line down here, that's gonna be my hypotenuse at 64. When I draw this all the way through until it intersects bingo over here, that was the magic for knowing where this line didn't do it, but that was the magic of knowing where this line intersected over here from the circle was concerned. It came out all the way around here, like that. That was my other point. Where it intersects here and here is important because those are going to be my two principal normal stresses. I already know that this was 80 from here to here, and if this from here to here, did I write the wrong one on there? Yeah, put that in the wrong spot. This is my 050. What am I thinking? And this is my 40 point right here because that's where it went through the line. So this is my 40 and 40 out to 80. That's where the center was. Knowing, so there's one point, there was the other point. Those are the 2 points that form my diameter. Draw the line between, comes through and dissects this, right, in this case, between the middle of these two. So now I know this is 40, this is 40, and I've got a little bit of leftover here. Don't know what it is yet. But what I'm trying to figure out now is what are my two principal stresses, right here and right here. How can I figure that out? Well, I already know the diameter, right, or the radius, right, 64. So I know that one principal stress is 40 plus 64.
104.
And I know the other principal stress is 64 minus 40, which gives me that negative value over here. So I just figured out my two principal stresses by looking at the diagram here. That's where I got the hypotenuse right here, the 64 from. I've got my principal stress right there, number 1. I got my principal stress number 2. And my angle, which is important, the last part right there, the 2 theta. That's this right here. Now the key is, what direction is it? It's from the x-axis up to, like this. I can do some quick math because I know the two legs and the tangent. Inverse tangent gives me 51.3 degrees. But remember, that is what? 2 theta, right? And we know the direction that we measured it in. Well, I went from here to get the original one, but we know that this was in a clockwise direction. That's why we put that clockwise on there. Remember, tell us what direction it goes. Because here's what you're going to do with that info. Now when you try to do the principal stress element, there we are. That's where we translated or rotated the stress element to match up. But that was 2 theta, so theta is 25.7. It's only half of that. I rotated my cube around, and I already told you we figured out these two values by knowing what the hypotenuse was. That's 64 plus the 40. So 104 in one direction and smaller in the other direction. 104 and 24. Notice what's on this element. When you look at the principal stresses, the principal normal stresses, there's no shears on this unit. That's the equivalent normal stress. And then you can do the same thing for the shear stresses. On the shear stresses, you got to look at the diagram. You'll notice here the maximums occur at these peaks of the circle. Here. And when you do the same sort of calculation, you've got to figure out the angle that you need to rotate the unit to. In this case, it's going to be half of the 38.7, which is the other half up here. It's this section over here. And we can do the simple math to know that it's 64 both ways. 64 both ways. So this is my shear element right here. So that's the maximum shear stresses for that given load. Your problems will be simple. They'll say, given a diagram, figure these out, or here's some data, figure out the values. Use Moore's circle to figure it out. Questions? Good, onward. If you want to do the rest of the math, the next 2 slides have it on there that show you the rest of the calculations that are done on Moore's circle overall. And that's just to give you the background if you want to look at it. But that's the summary answer of what we were looking for. That diagram, those are the shear principal stresses and the normal stresses. That's the Moore's circle for that given problem. All right, stand up. Woo! This time you got to turn around. Oh man, my head's spinning a little already. All right, sit down. Stresses are 3D though, don't forget they're in 3 dimensions, you're gonna find them all over the place. And then for 3D stresses, you gotta work out the 3 different dimensional groupings of the stresses in order to determine what you're looking for and identify the maximum shear stress out of all of that. Also, elastic strain is good to know. We already talked about modulus elasticity. That's the ratio between the stress and the strain, otherwise known as the slope of the curve over there. Axial direction strain, if I'm trying to deal with it, that's what it would look like. But if I'm looking for the radial strain, I have to include one more concept, Poisson's ratio. What did that tell us? Yes?
When you apply a force in one direction, so if you're pulling it apart, the diameter is gonna get smaller. If you're pushing it together, it'll change in the other direction. You're changing the cross section, if that makes sense.
It's the proportion of squish to stretch. That's exactly what we were trying to say. Okay? So if I squeeze it, it expands. If I stretch it, it constricts. Poisson's ratio tells us what the relationship is between the two. Classic problem. They'll give you a rod. They'll say it's under a load, either compressive or tensile stress. And they'll say, what was the percent change in its dimension? Or how much did it displace? Pick one. You need to start off with the force per unit area calculation to figure out what you've got. So then you can then come over here and use this equation right here with Poisson's ratio and the relationship between the stress strain and the modulus elasticity. So you have 2 givens, which will be Poisson's ratio and the modulus. You also have either given in the problem or they put in the table that's at the back, or the cheat sheet that you get for this one. Poisson's ratio. If you're still working strain, don't forget strain is also in 3 dimensions. We're talking about 3-dimensional things. And also there is a complementary Hooke's law for shear stress, just like normal stress up there, except instead of the big E, we've got the modulus rigidity, the big G that we use in there. There's a relationship between the two. This is a nice little equation. Modulus elasticity is 2 times the modulus rigidity. What's that value? Poisson's ratio. That's that relationship between squish and stretch. Okay? So, they can be related to one another. When you distribute them evenly, like you see right there, that's the force per unit area. Shear stress is the shear force per unit area when no bending is present. Now that brings us to beams. So classically, the beams are rectangular things that they're going to give you. Remember when we have those beams, when we put them under load, we're going to start talking about the stresses that are in that beam and where it occurs across that beam. There's a thing called a neutral axis on the beam. Great image down there at the bottom, kind of gives you what I'm saying. That line that he drew in the center, as much as he bends it, that line stays the same. So what's the stress at the top? Positive or negative? Positive compression. What's at the bottom? Negative or tension. And you can immediately draw the profile across that if it's a symmetric square or a symmetric beam. What's the profile look like? Of shear stresses? Just stresses, period.
Looking a flat line, doesn't it?
Flat line? Ooh. Oh, we're gonna huddle at the AME department meeting tomorrow. Or Monday. So, if this is my beam, and the profile of my beam, I set it so that my beam, on my neutral axis of the beam, sits right there at this point. The tension, see, in his case right here, I've got all of these in compression, I've got all of these in tension. It's 0 at the neutral axis, and it gets bigger and bigger and bigger the further way out. So the maximum normal stress that occurs in this beam is on either the top or the bottom. Once in compression, once in tension. Remember, from a design standpoint, knowing how your material deals with those sorts of things, it goes a long way to how you're going to design your stuff, which dictates what type of material you're going to use. Okay, materials that don't do well in tension but do okay in compression, you don't want to bend them like that. Why? They'll fracture at the bottom. Once they fracture on the bottom, the crack starts to propagate, and that whole thing goes. So that's why you got to pick the right material. Mechanical engineers, that's your bread and butter. Okay, it's especially those who want to become FEs or PEs, okay? So that's the basics of what we're talking about here, about that neutral plane and that neutral axis. Now, life isn't always that easy. Not every beam is perfectly symmetrical, and so you need to be able a couple of tricks up your sleeve to deal with those on the FE exam. But the basic ones they're gonna give you are things like this, and ask questions about the various stresses that are in that beam. Where are the stresses? What are the values? And they're gonna give you some diagrams, or they're gonna ask you to calculate something based on the formulas I'll show you in just a second. That's the diagram right there. So in this case, there's the compression, there's that tension that's on the other one. Depending on how you're bending it, and then centroid. To do that, we need to know some other things about the material. One of the things besides the area is that second moment, or the moment of inertia, about the axis, because we need that to do the rest of the math, to figure out how it's located and where that stress occurs in that beam overall. Those are the formulas basically for the normal stress, the bending stress that occurs. Magnitude of the largest stresses that we already said occur at these points, and so you're going to use the value essentially that's measured all the way off of that neutral axis all the way to the wall. So now that kind of gives you a hint. We can have an axis that maybe is offset, meaning our profile of our material could be a different shape. So we can move that neutral axis somewhere else and use a common equation to figure out what our maximum stress is. Caution. Everything I'm talking about here so far is based off of the fact that your textbooks and stuff were generally Shigley and the other ones that talked about it with these symbols. When we look at your cheat sheet here in a minute at the very end of our conversation, I'll try to point out where the symbols are a little bit different. The formulas are identical, believe me, trust me, honestly, they're identical. They just use a slightly different variable on the equation on your cheat sheet. It'll be very obvious to you as soon as you look at it. But if you're looking and you go back to a textbook to find this stuff, the formulas you see here will match better with your Shigley, if you're looking for the background information. If you're looking at any of these here, they're using what's on the exam, and like I said, the formulas are the same. They'll just put a slightly different variable every once in a while into a couple of the values. I'll give you an example here in a moment on one of the slides. Don't forget bending. So, normal stresses, that's called pure bending if that's the only thing that's on there. So the effect of axial torsion and shear loads are often assumed to have minimal effect on there. So in most cases, you want to keep things simple on the exam. They will give you the muddy data if you need it. They have distilled these down just the simplest part of the question. So they won't try to muddy the waters. They'll say things like, for a simple bending beam, boom, all of those assumptions now apply. You don't need to worry about all the gobbledygook that goes along with it. Everything obeys Hooke's law. We already talked about symmetry. So it'll be obvious that you're going to work on something that won't have the nice clean symmetry, because what they'll do is they'll give you a profile that looks like this. They'll give you that profile, meaning here is a T-beam. Bend it. Well, okay, my axis of symmetry isn't like the same as the rectangular one. I got to figure it out by knowing the two moments of inertia and so forth. I figure out that there's my neutral axis. My neutral axis is offset when I look at the two pieces, and you got to do a little bit extra math on those. The formulas are given to you in the cheat sheets. Also, the plane cross section, this one right here. What we're saying there is when we bend these things, we're not dealing with any of that Poisson stuff where the profile physically changes. If it's rectangular, it'll stay rectangular and bend, so you don't need to worry about all the other math that goes along with those sort of changes. Here's an example. Oh, it's a T-beam. Look at that. I wonder why I was thinking of that. If you're trying to deal with something like this, again, simplify, people. Remember how you solve these problems is you see something else you recognize. I look at that. What do you see? Two rectangles. I see a big flat one on top. I see a tall skinny one on the bottom. Bingo, that was your ticket to making this problem way easier, because now you simply do the math for the two rectangles and then put it all together. Don't struggle desperately trying to figure out the moment of inertia for a T-shaped object. If you know the data and the information associated with this, you can start to figure out what the deflection of that beam is. In this particular case, there's the two rectangles we just talked about. You have a total area, you have some of the moments around those, so you can take the 1 and 2 areas there and figure those two out for the sum of the moments. And you have a differential or offset from that neutral axis. C1 goes to the top, C2 goes to the bottom, gives you a sense for how it splits it all up. There's that moment of inertia, the second moment of the area. Now, you're going to need these to calculate stuff. These are not on your mechanics cheat sheet. They're gonna be on an earlier cheat sheet where you learned or had the review associated with the statics and dynamics and all the other basic principles. They have little tables of these. So you got lots of them to choose from. This is a classic one for a rectangle, 1/2 BH cubed. All right, that's a good one maybe just to remember in life for these sorts of things, because most of your problems will be rectangles or circles. All right, you'll need that moment of inertia. Now you'll notice we did that for the two separate pieces. So we know where that the values are for those two different chunks, because then we can use that information in our formulas here in just a few moments. This is the formula I showed you a few slides ago, where the stress based off of the moment and where that force is applied, or where you're looking at it based off of the neutral axis over, there it is, moment of inertia. So you can identify the stress at that point. So if they say, what's the stress at the top of this beam? C1 would be that maximum distance from there to there. M would be that force or the moment that's put on it, or the moment, and then I is the modulus elasticity you're dealing with. So those are the values up there. You can see the, one other thing is the parallel axis theorem associated with those moments. Where, right here, the second moment right here about the area that you want, and the second moment about the area, any parallel spot. That's based off of the area times d squared, differential distance that you're looking for. So you can move that moment of inertia to a different spot and be able to use that for that particular location. And so that's all this problem did, is it take those parallel rectangles, figuring out that maximum tensile stress at the surface, or figuring out the maximum compressive stress at the bottom. You'll notice those values C right there are those maximum distances on either direction. And there's the two different moments right there. Well, the same moments because you're using the combined moment of inertia. What if you're bending not two rectangles of the same material, but you're bending two things of different material? It's essentially the same problem. The difference here is you're changing the modulus of elasticity for the materials. So the trick to this is put everything in apples, because you have apples and oranges right now. Convert everything to apples. So pick one, use the ratio of the moduli in order to get it in terms of the same one. So what you see here, what we're physically, in your mind's eye here, what you're doing is you're taking two different materials, you're finding an equivalent modulus of the other one, and now this is what it looks like when you're done. Essentially, that material on the top is so strong and stiff, it acts like an even bigger plate of the same material on the bottom. So you're simply trying to make life easy by putting one in terms of the other. Okay, so if I had two different moduli, there's my ratio between the two of them, and I can slip that ratio inside and do the same math that I just did on the previous slide, because it looks like two rectangles to me. That's the only difference. Don't let composites or two different materials throw you for a loop. Just put one in terms of the other. There's the shear stresses and beams overall, just so you can get the whole sense. For example, for a distributed load, that's what the unit stress, the stress unit, basic stress unit, is what you're going to use when you're doing the analysis. You work on integrating this over the entire length of the beam, and then you can determine what the various shear stresses are at different positions when you go from one to another. That's just the same diagram with the formulas that go along with it. So that's representing what we started scribbling on the far side over there. Transverse shear, always accompanied by a bending stress. You'll need the first moment area, but that's the formula for the first moment area. But that's the transverse shear formula right there. You have that also in your cheat sheet. And there's for a rectangular beam, the simplified versions of those same equations. Notice what's not right here. What's absent right here? What does not exist at the surface of the beam? What did we not draw on this beam whatsoever? What physically doesn't exist in the beam at the surfaces?
Material.
Well, keep going. If there's no material there, can I have a shear stress?
No.
It was a simple question, it wasn't a trick question. There's no shear stress, you notice, at the surface of the material. That's one that also slips by, just slips by again. It slips by on occasion that when you're looking at different things and you're trying to identify stuff, remember, there's no shear stress at the surface because there's no other crystalline structure beyond the surface to have shear with, by definition. Okay? No shear stress at the surfaces. Okay, by the way, there are shear stress formulas that have already been put together for various profiles. Again, these show up in a different cheat sheet. You don't have this in the mechanics of materials sheet. This is just showing you that we've got a couple of already pre-done formulas for you based off the areas. This is the ugliest one. That's based off the I-beam. If they're going to give that to you, they'll give it to you. Otherwise, you don't have it available to you right off the bat. Woo! Box, box, box. You're teachable. Look at this. I didn't have to say it this time. All right, this is a slightly longer one because we're about halfway through already. Oh my gosh, and we're halfway through? Yeah, this is going to be fast. I warned you. Kind of a quiet group on a Friday. Out of this group, who really wants to become a PE? 1, 2, 3, 4, 5, 6, 7, 8, 9. Actually, wow, that's a big group. I commend you. That's great stuff. You're aspiring to what Professor Collins did for a living for many years. And the ability to get a really cool seal from the state of Washington if you stay here. So you can emboss your seal on various diagrams, and you'll be the one they sue when the bridge falls down. So it's really wickedly cool. Every other engineer in your company will work for you. They'll also seek you out for that that understudy, you know, for that work as a engineer in training type thing. So you can sit down. I'm sorry. You can sign that stuff off. I'm impressed. I'm very impressed. So I wish you all luck. For the rest of you, I have no idea why you're doing the FE. My experience was I came out of college. I was in the ROTC program, which obviously paid for my college, which was a good deal, and I was picked up for the nuclear power program, which meant I needed to go off to nuclear power training right off the bat. So I graduated and I flew out. I was gone. I went to Florida almost instantaneously because my class started weeks after we graduated. So I didn't even blink an eye about an FE because I was thinking, oh, I've got a job to do. I've got to go deal with that. So I'm in 12, 15 years into the Navy now, and at this clock I'm looking back and going, wow, what am I going to do for another career? And I stuck around for 27 years total, but about 15 I was looking at it again going, man, maybe I could become a hardcore engineer again and just go back and do that sort of stuff for a living. What, you mean I have to go back and take the FE? Are you kidding me? No, I'm not going to do that. And about year 20, I went and said, wow, I should have taken the FE right out of college because then I would have had options later. So I encourage you, and I applaud you, folks who are not necessarily thinking of PE right now but are taking it anyway, do it as soon as you get out of here because all of this stuff will be painfully fresh and you can regurgitate all over the exam and be able to get something out of it and say, hey, I got the FE. And then you can decide what you want to do with it later. You got another option. So like in my case, I already had an option, so I didn't need to worry about it. But if you don't have other options on the table right now, it's a great way to go to get the FE taken care of. So again, I applaud you. Quiet group. Okay. Second half, ready? Am I going slow enough? Okay, beams. So, square rectangular beams, that was easy math. Other beams, math gets a little bit more complicated. This particular problem is way more complicated than you're going to get on the exam, but it's useful for its constituent pieces. So it's worth taking a look at it again real quick to understand where we got it from. If you have a beam and you know the general dimensions on here, and you're getting ready to take this beam and put it under some sort of load with simple supports at either end, there's that free body diagram. Wow, you got to practice those, people. If you get that free body diagram, and I have this as a profile, the question becomes, what are the loads at point, fill in the blank. All right, so that part of this whole question is very fair game. You won't be doing all the parts that we did in this one, but any one of those parts could be something you could ask. Now, two quick things to notice. that's the actual profile. This is the profile we ended up using. What do you notice between these two?
Got rid of the rounded corners.
Okay, engineers simplified. We got rid of the rounded corners and we treated this whole overall section as a big rectangle. And the beauty of that is it will work out. The answers will be minusculely different than one another. And if you haven't caught on in your practice exams, which you've been taking already, the answers they give you are not the exact answers. What? Yes, they're not the exact answers. They will say, which answer most closely matches the value of, and then the problem. Your answer may be 46.894, and they give you an answer of 48, 50, 102, and 9. What's the right answer? Most closely, 48. So, you see a problem like this, you immediately simplify it, do the best you can to solve it, and then find the answer that's closest to yours. Okay, so if Professor Collins hadn't told you that, I'm telling you that. That's the way these things work. So that's the other danger to this. Some people who have taken other exams, SAT and others, you do the reverse engineer sort of thing. You get yourself something in the ballpark and search and hunt for something that has all the decimal places you think are there, and you pick that one because you're just guessing. You can't do that on this one. It's got to be in the ballpark, and you got to know that you're in the ballpark for it to work in the first place. So given that beam, there's your free body diagram for that beam. That's what the load and shear forces look like. If that didn't instinctually come to you, practice a little bit more. I need the moment of inertia, and I know for different rectangles I can do that. That's that BH cubed over 12. I can work that together with the two different ones and put them all together, figuring out, oh, I know also from the fact, because it's symmetrical, that the neutral axis is right here. That makes some of the problem a little bit easier. And then you can go through and work out the values at different points. So when you do this all the way through, for example, at this particular point, there's A. You can see what the end state forces are associated with the loads that are throughout the beam based off of what you put in here for the endpoints of those summations. Then when you do the final shear stress calculations, you can see the VQ over IB on each one of these right here. You can figure out at any one of those points to understand how much shear stress is there. Hopefully it makes sense that there's no shear stress at the surface. Okay, I say that because when you do the math and if it doesn't come out to 0, you know you did something wrong. I'm trying to point that out as a check and balance tool. If you know certain things that are just facts and you do the math real quick, it doesn't come out, you got the wrong formula. Go back and grab a different formula. And this is kind of interesting because you can see that the maximum shear stress occurs right here at the beam. Almost all of it here, practically none of it on the ends. That's why now you can see why we simplified. You're not going to change the answer because the shear stresses are so tiny depending on where you are on the outer edges of the flanges, which is why I-beams work so well. There's the normal stresses or the bending stresses. Here's another one to keep in mind. When I drew the diagram over there, at the neutral axis, what was the normal stress?
0.
Say it with some confidence. Absolutely 0. Look at this. If it's symmetrical, there is no normal stress on there. Do the math. If you do the math and you do a formula and you don't get 0 for the neutral axis, you did something wrong. Go back and check your math and go get a different formula. Nobody's going to tell you this. This is a hint you need to know about before you walk in there thinking, oh yeah, I got a quick check. It worked. Finish that problem off. If you did all the other points for all other stresses, you're going to use those other quick formulas that are going to put them all together. Against most of these formulas are going to give it to you. We'll get that in a few minutes. You don't like bending things, well then twist them. So when you do that, you need to deal with the angular displacement or the angular rotation. So there's your formula. You'll notice in this case we're using the modulus of rigidity. Okay? Think of it, the modulus of rigidity on the side of a spring. That's the G shows up in springs a lot. Okay, so when we talk, I get to come and chat with you one more time. Design, when we talk about design and springs, the G shows up a lot. Kind of makes sense, rigidity. Its ability to kind of resist that flexation and go back to its original spot. In this case, when you twist something like that, you need to figure out how much it rotates. Well, that angle is that ratio between the polar moment of inertia or the second moment of area, the J, and the modulus rigidity along with the torque and how long the beam is. All right? Essentially, that shows up being the same equation you use when you start talking about torsional springs, because it's the same principle. We just add one more spring constant in there so you can call it a spring constant. But this tells you how much you're going to displace it. If you're talking about the stresses that are in there, the torsional stress, maximum torsional stress, what do you think the maximum torsional stress is? Look at the formula. What makes this biggest? That's fixed. That's a known single value. Only thing that makes it big is radius. Where is the torsion or the shear stress in a torsional beam? 0. See how you're checking these things? Just by looking at the formula, you can tell right off the bat what those two answers should be. And if your calculation comes up with something other than that, you know you're on the wrong path. Stretch. This time, shake it out. Arms. Come on. Let's hear a little. Now, there we go. That's the right attitude. You're going to be successful in the exam. Sit down.
I gotta do some
A couple of quick assumptions for the torsion stuff, by the way. This applies again, unless they tell you otherwise. This is your expectation that it's pure torque. Hooke's law still obeys. Radial lines remain straight. That's another interesting one. When I say that, radial lines remain straight, what do you think I mean?
We draw a circular cross section with radial lines out from it. They're not getting closer.
Excellent. Excellent. And in case you didn't understand what he just said, we're referring to this sort of thing. If I chopped it in half while I'm twisting it, if I were to give you a drew a line with a marker on here, those lines would all remain straight. They wouldn't go like this, depending on which way I'm stretching or twisting it. All right? That's a much harder, complex mathematical solution going forward. And mechanically, most of our materials will be so close to this straight that they meet most of our needs. That's why most of your formulas are based off of that. And that's why this is a pretty big deal right here. Okay? They won't be asking you the complex stuff. They're going to keep it simple, so you don't even need to worry about it, which means you just use one of the formulas we've given you. Power, speed, and torque. I only bring this up to make sure you've got this reference. Every once in a while, people kind of get wrapped around the axle if they ask you in different units. Obviously, H in this case is power in watts. There's T, which is torque, and what's that one? Omega, thank you. Angular velocity up here. And if you're trying to convert between the two, that's the relationship, 9.55, and in the angular velocity in revolutions per minute. And just because I could never pass up an opportunity to pick on our US customary units of horsepower, quite literally, that's where it came from, if you didn't remember that. Yeah. In 1 second, moving 550 pounds, who picked that one? Lifting it up 1 foot, which is a total of 12 inches, base 12, by a horse, constitutes 1 horsepower. Give me a break. Oh my God. Anyhow, that's the formula if you want to use horsepower. Here's a torsion example, not dissimilar to your very first free body diagram. In this case, I've got a single shaft. I've got a couple of pulleys that have been keyed mechanically to the shaft. And you'll notice I've got loads on here. What do you notice about those loads? What?
They're going to create a torque.
They create a torque because they're different. You'll notice I have 500 and 100, which means I have an end state torque of about 100 foot-pounds in that other direction at a certain distance, which is the radius of the gear. Same over here. So that's how I'm applying torques to a shaft. So don't let that scare you on a problem. All you're doing is putting a torque on there. And rather than saying, here's a vector and there's a torque of 100, it's here's a pulley and here's the load on it. You, the engineer, go, piece of cake. Figure it out. Now I know what the torque is on there to be able to figure it out. Go to the next point of how much am I twisting this shaft. So if you do all that, that's what your free body diagram should look like. Now recognize it's in 3 dimensions. I have no forces that are going axially, so I don't need to worry about those. But I do in the other 2, in this case, the Y and the Z axis. So I have to draw out my free body diagram. I've got reaction forces at the bearing points. Those bearing points also have the horizontal reaction forces keeping it from sliding off the bearings. And then I have net loads and torques that are occurring at both of those places. Notice in this case, 500 plus 100 makes 600 pounds of downward force. Makes sense, that's the belt pulling on there. 1,200, I got 1,200 foot-pounds force pulling on it in that direction, so I have to keep it from moving. But then I also have a resultant torque on here. Figure out the final torque, then you can figure out how much you're twisting from place to place. That's what the two diagrams would look like when they're separated in just the individual planes. So there's your moment diagram that goes along with it. Now you could try to do these individually, but if you put them in a single dimension, you combine them for the final vectors, so those two directions, and you combine them simply by using a little Pythagorean theorem, you now have the total moments that you can use for figuring out the final calculations. So that means you can figure out what the total normal force is, or the normal stress and the shear stress is on the shaft. You know, I always take silence for acquiescence, right? 100% comprehension and complete understanding. See? See how it works? That finishes, this is what I was just talking about here, taking those two directions. You can figure everything out this way, but if you figure them out by combining them, then you can use the combined forces in your calculations. In this case, you can figure out what that shear stress is, the primary shear stress, primary normal stress, let me back up. Primary normal stress in one direction, primary normal stress in the other direction. So those are the two primary stresses that we're putting on there. And then the shear stress at the bottom. If that wasn't enough, you will be asked about things called closed thin-walled tubes, otherwise known as hollow thin-walled shafts. Who knows? They're going to use both phrases. So think of this as a pipe that's going to get twisted. The other thing they're going to ask you about are cylinders that are pressurized. They all have their origins in the same math I'm going to show you, and the calculation the solutions that you work on are straightforward. You just need to use the formulas that I'm sticking up there and plug in the numbers to calculate what those shear forces or those normal forces are. Okay? So the first one is that thin-walled tube. Mathematically, what you're doing is you're taking something that has an inner and outer radius, so overall thickness T here, and you're looking at the individual units, the unit stress cube. You're doing it all the way around there, integrating it for the whole thing. And from there, you're going to figure out what your forces are. That A that you see on here, that's the, where's the median line? There it is right there. There's the median line in the center, and that we're going to use that to, when we do the final calculations here. When it comes to these, the shear stress, that's the formula that you have in your book or your cheat sheet, and the angular twist, how much it's going to rotate, is given by this big ugly formula right here, where you can see the torsion, you can see that modulus of rigidity, there's the area, there's the thickness of the wall. This is the area at the median, by the way, based off the median line, and the length of the median line. So I'm not measuring the outer wall, I'm not measuring the inner wall, I'm measuring the median line. That's the value I use to make this calculation. So those are just plug and play. So now you know what the shear stress is that's going to be in that pipe and what the overall rotation or the angular displacement is going to be. When you put them in the formula, just so you can kind of see what's going on here, there is the maximum shear stress right here. Well, that's using two different methods, but I won't worry about that. You're going to be given the formulas, and these are the formulas that you want to end up just using as the end state equations. Pressurized cylinders, like I said, was the other one. This is where it starts from. What we do is we take that same thin-walled sort of concept, but this time we make the wall thicker. Okay, great, I get that. So math's going to be a little bit different. And I'm going to have pressure forces that I'm dealing with either on the inside or the outside. So we started off from a theoretical standpoint trying to figure out the tangential and radial stresses here. By the way, tangential stress is also known as hoop stress. Still don't know what I'm talking about. If anyone's going to hula hoop, you take the hoop, put it around your waist. Those are the stresses that are around the hoop itself. Another way of looking at it is anybody loves drinking wine or other alcoholic beverages. We tend to put things, you do. You put things in things called barrels. Those barrels are held together. Those different sheaves of wood are held together by hoops. that hold the whole barrel together, keep it structural, while your grape beverage ferments and pressurizes the barrel. That's what keeps the barrel from blowing up, are the hoops. Hoop stresses. Tangential hoop stresses and radial stresses are orthogonal or right angled to one another. And we can model them as principal stress elements. That's where you do this little thing again. Then you go integrate it over the entire area. Doing that, putting it all together, there is a special case of something like a CO2 cylinder. So when they say I have a pressurized cylinder, it's essentially saying I have a cylinder with a gas in it. Right? Whether it's carbon dioxide for your beverage, whether it is argon for welding, whether it is CO2 in a fire extinguisher. Okay? We're just talking about a pressurized cylinder. In that particular case, what we're saying is between the two, I don't have an outside pressure. I know we have a pressure here, but when they're making a relationship between the two, the atmospheric pressure is our 0 point. And the pressure inside, because the gauge pressure is a pressure based off of atmospheric pressure, that's why the pressure outside is 0. Mathematically now, those big ugly equations start to simplify. We're not quite done. They simplify even further to this right here because I'm more worried about the maximum. I could really care less about the medium stresses. I'm really worried about whether this will fail, meaning what's your maximum stress on it. So that's the formula for the maximum hoop stress or the maximum radial stress. Interesting. The maximum radial stress is what? It's the pressure of the cylinder. Whatever the pressure is on the inside is the maximum radial stress that I'm putting in there. Kind of makes sense. Again, this is a quick check and balance in these formulas, because that's a big ugly formula you'll be using to figure these things out. And if you're looking at it from the standpoint of what's the radial stress, which is this one down here, it simplifies down to simply the interior pressure of the cylinder. Whereas the hoop stress is a little more complicated. You got to take into account the radii, inner and outer radii, times the pressure that's in the cylinder. Yes?
So to use the simplified equations, it has to be atmospheric, and we have to use gauge pressure.
Okay, so what they'll say is that the cylinder is pressurized to 100 pounds. That's the formula you're going to use, because the outside pressure is 0, and they're referencing atmospheric pressure for the pressurized cylinder. Now, okay, that was for the walls. If and when I seal this to a fully sealed cylinder, and they'll say that cylinders are closed ends, then I get a longitudinal stress that's also in there. So I did radial stress, I did hoop stress, but longitudinal stress is this way. So once I cap the ends now, this pipe is now under a tension, essentially, because the pressure is trying to push the caps out, the caps are trying to push on the walls are trying to stretch out, so it's putting the whole thing. So there's a formula for the axial stress, which is also simply based on how much pressure is inside the cylinder and the ratio of the radii for the inner and outer walls. So it really does get simple. They won't ask it quite this simple, they'll give you one more step in between. And usually it's a material-based sort of question where you need to do one formula like our simple force per unit area type thing in order to get the value needed here or something like that. And the last category of this is what's called a thin-walled vessel. If the vessel wall thickness is 1/10 or less of the radius, yes?
Radius?
What?
What radius?
Of the, and it doesn't really matter because when you do the calculation, if the overall thickness is 1/10, pick one of the two. If it's less than 1/10, then you're dealing with what's called a thin-walled vessel. And there's a simplified formula for that, for dealing with those stresses. And you'll notice how they simplify out right here. Diameter times thickness, not radius to radius. So we did some simplification in our math up here to give you two simplified formulas, well, three simplified formulas for the three stresses that occur in a thin-walled vessel. Vessel, meaning it's fully contained, it just has a really, really thin wall. So the thickness is 1/10 of, pick one of the two radii. These formulas are given to you. And then just a couple of slides, when you would like to look at them, doing exactly this. Again, this slide the math on here, actually, this problem is pretty close to what you can get on the exam. Just pick one piece of it. And trying to figure out what the stress is given a 12 kpsi and a thin-walled vessel. So you're just gonna use that formula, figure out your tangential stress, and then there's your radial stress based off the pressure. Okay? Not very complex. It's pretty straightforward. Oh my gosh. What if you make it cold or hot? Is that a problem? Can be, and you need to be able to deal with it. Question may show up. Temperature change of X, given these properties of the material, what's the change in dimensionality? So, obviously, for a straight bar that's been welded or put between two walls of constraint of some sort, and all of a sudden it gets really hot in that space, the temperature go up, obviously it wants to expand. Unfortunately, if the walls constrain it, the beam is now under compression. So one question could be about the forces that are on there. And in this case, you can see we've got that formula set up for essentially what is the forces or the stresses in this case. But we need to take into account this thing called the thermal expansion. And we have a coefficient for that. So you'll notice the coefficient of thermal expansion times the temperature shows up in the formula so that you can relate your stress and strain together when the temperature changes. So in this case, for a given, it's a delta T to be clear. For a given delta T and a thermal expansion ratio that you've been given, standard modulus elasticity, what was that? Poisson's ratio. Bing, 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 all out of the table. You can figure out what the stress was in that particular number. This is classic. This is classically the way they're going to ask that question about temperature changes in the material condition as it changes. Okay, that's just a quick table of some of them, what I'm talking about. They'll give you this data. We're going to look at this in just a few moments in your cheat sheet, but they give you this data for different values of Celsius or Fahrenheit. That's just a couple of examples so you can see what goes on and how they are going to play out. Woo! Now admit it, you need this. You like standing up. Yeah. God, I gotta listen to this guy for 2 hours. Just let me stand up at least. La, 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 la.
Exactly.
Wait a sec, you're doing the easy stuff. You're just sitting there. I'm carrying all the water. Good enough? You good? All right, here we go. Okay. So when we load these beams, they're going to deflect. Classic question. How much? Where? It's going to cause a problem. Are my bearings going to fry? You start off by just talking about how the bearings are going to flex, or not bearings, but the beams are going to flex. And we have lots of things that go into that. This slide's just trying to give you a sort of a background, a setup for the fact that the beams can do lots of different things, all based on the material properties. You need to keep in mind the material properties that they give you so that you can determine what they're going to do. This is really beyond the scope of what we're talking about, but this is just a quick reminder that sometimes you have material that has a linear spring constant to it, so it bends nice and straightforward and comes back. Some that have a what's called a nonlinear or stiffening spring or a softening spring here, where the more you push it, the weaker it gets. Lots of different applications for that. You're not so much worried about the springs, but the fact that I'm going to get deflection out of there, and this all kind of links together with that conversation. The relationship between force and deflection is a differential. That just so happens that differential spring constant is that dF over dy, that overall displacement. So there's that spring constant I was talking about earlier that always shows up in these conversations again. That's where the spring constant comes from, force for the deflection for a given known material. If you had a problem that's going to do that, they will give you that, or they'll say what the spring constant is, and then you need to apply it accordingly. You know what that is, and you can immediately, if you know what the displacement was, know what the force is, so you can put it into a stress equation and figure out what the stresses were. Axially loaded stiffness, either in tension or compression of a uniform bar. That axially loaded stiffness comes within the differential, or I'm sorry, the displacement from this equation right here. Again, this is related to that spring constant, but instead of that flexion that occurs, we're talking about the springiness when it comes to an axial loaded condition. Now, the angular deflection of a solid thing subjected to twisting. Remember, we did this earlier, and that was that formula we came up with for that angular deflection. Well, here's where you get that spring constant I was talking about. And it's this formula right here. When we got these things, you'll notice it's related to that modulus of rigidity, that polar moment, and the length. And that's where we got that spring constant value from. So it's the same formula in the earlier slides. We just give it a different name when we relate it to its angular displacement. So let's talk about bending and deflection. So when I take something and I bend it with put a load force on it, I create a moment, and that moment then deflects or bends that particular material. And how much it bends, we have to have that moment modulus of elasticity in there to be able to have some sense for what the material properties are. That's what that is in that formula. So you do a little math based off of that. There's the derivatives that we were talking about, and the second derivative that's giving you that displacement. So the slope of the beam, the angular slope of the beam at any point is the first derivative. If the slope's very small, the denominator is 1, you can combine those all together, and you get a simplified formula right here. There's that second derivative based off of the original properties of the material and how long or where that displacement occurs. So let's put that into practice. If you start with that shear force, the derivative of the shear force gives you that displacement, and these successive differentials talk about the different aspects of whether you've got how much the displacement is of the movement. That's this consolidated chart of everything I've just been talking about, and you mentioned it several times before. Starting with a beam with a uniform distribution, or whatever distribution, with reaction forces simply supported. What is, then they'll ask you, fill in the blanks. What's the shear diagram? What's the moment diagram? What's the displacement diagram? Ultimately, what's the deflection down here? So this was the slope, and here's the deflection. And the cool part about this is once you have these tricks, you differentiate if you're going that way, you integrate it if you're going this way. Integration is area under the curve. So just look at the graph before and just say, what's the area doing? Is it getting more area? Is it getting less area? Is it constant area? Going the other way, what's the slope of the line? So if you know the moment diagram, and I know the slope right here is a positive value of something, but the slope is constantly decreasing, and now the slope is 0. Oh, looks like I'm dictating this line right here. I am, because now then the slope is negative, and the negative getting bigger and bigger and bigger and bigger negative. So these diagrams are painfully easy. You just need to remind yourself of those differences, and you need to remind yourself of how you did this diagram up here so you can put values on these graphs now. Okay? And another nice thing is, you're going to see in a moment, we have the formulas given to you for different types of loads. If you know that, and you start, let's say, here, you can figure everything else out. Because once you have this formula, you'll either differentiate it or you'll integrate it. Problem solved. Like this. Like this. Click. There we go. There's a beam. Here's the load distribution given by, or a moment, given by a formula based off of that load of this given constant load. What's the maximum deflection? Okay, well that was easy. If I'm given this, and I know which way I want to go, up or down, I'm either going to differentiate it or integrate it. So in this particular case, I started here because I gave you the moment formula, right? If I'm trying to find the deflection, I've got to differentiate it or integrate it twice. And I can give you this graph right here for the overall deflection. And answer the final question at point and pick it. What is the deflection? What's based off of this? Which is based off of this? This is what you're given. You figure that out. Now, sometimes they'll ask you not just for a number, they'll ask you for what the formula is for the deflection. So, given this previous slide, given this formula right here, put that in the place of what this is right here and differentiate it twice with relationship to x. I'm sorry, integrate it twice with relation to x, and you'll have the displacement formula. And that's what they're asking for. They'll give you 4 formulas. Choose the formula most closely matching the correct formula. And you pick the one that is correct. And all you did was take this and integrate it twice. In this case, if we did it mathematically, you can put the whole thing in there. In this case, you also need to put a constant of integration in there to do the math completely. You'd set the boundary conditions at 0, pick a spot, in this case it's 0 equal x. So the boundary conditions for that mean that there's no displacement in y, because it's fixed to that particular side. Then you can make the constant go away and learn that the constant C2 is 0, and your formulas become even easier. These formulas right here that you see there are in the table they give you. So they've already done all the hard work, you just need to know which one to use and how to use it. So that ultimately is the displacement, maximum displacement on there. And this is our angular or slope displacement, depending on at a specific point along the beam at position L. And when it comes to the final solutions, there are lots of different ways of solving this. The only one I'm going to point out is the easiest one on this list, which is called superposition. What I'm saying there is, previous slide, your problem was beam, distributed load, and that's all you had. But what if you had a distributed load and a concentrated load right about here? Oh, that hurt. What did we do with the T-beam?
Simplify.
By doing what? What did we do with the T-beam? How did we simplify it?
2 rectangles.
We saw 2 rectangles and simplified it by that. In this case, if you can see through the chaff here, if you can see with the confusion, I have a distributed load and a point load. Do one at a time. Take the point load out, do the distributed load with the formulas you already know. Great. Flush that. Put the single load on there. Do the formula with the solution with the formula you know. Then go back and slap the two together. Final answer. That's what superposition is. So lots of different ways of doing it. I recommend superposition. It's the easiest way if they have any of those problems that are going to deal with that. Likely not. The problems are pretty straightforward when you only have 3 minutes, but there's the example I'm just talking about. It looks pretty simple. It is simple. Don't let it throw you off. Just imagine making this one go away for a moment, calculate it, then make this one go away and calculate it. Yes.
Do they give us tables of those conditions?
I'll show you those in just a minute, okay? Because I want to make sure you see what those are all about.
Okay, thanks.
So with the superposition, this is the half where they have some of the formulas that are already used in your free body diagram to figure out ultimately the final deflection. There's the formula right there for that final deflection from A to B. This is deflection from B to C. Why do you suppose I have 2 formulas for that condition? Why don't I have one formula for the entire displacement?
Was it because it's not in the center?
Almost. You said it's not in the center. That should give you a hint.
The load B?
What about load B?
Has a different deflection from A to B than B to C.
Yes, because of that singularity function we talked about earlier, this constitutes a break in the formula for the load equation. So there is not a contiguous formula from here all the way across the beam. That break means there's essentially a break right here. Now in this case, those 2 points tend to come together, but this curve and this curve are defined by 2 different curves. Completely different curves. That's why I have 2 different formulas. And instinctually it makes sense because it's offset. So it wasn't in the center. If it were in the center, I could technically have 2 formulas, but they'd be identical. They'd both be parabolas that make this out. But these are 2 distinctly different parabolas right now. Then solve it over here. Same free body diagram, but with my new load forces on there that are separate. So I go through and I grab whatever formulas that they give me and that I can use to make this easier. There's my maximum displacement with this. We'll have 2 formulas here. I have 1 formula here. What do you think I do with them? What? Add them together. Adam and Eve. Add them together. There you go. You just add them together. So in the case from A to B and B to C, you can see this part right here. That's the same part from the right-hand part of the equation. And these are the 2 different equations I use for up to that load force B and over to the other side. So my end state becomes this big old equation right here with the polynomials in it. Polynomials? Ugh. They give them to you. Life is now easy. You just need to pick the right one. Superposition. Woo! Callie's navigator, he finally stood up. He was giving me a hard time. He was just sitting down staring at me last time. Good call. Okay, engines in sight. Last couple of slides, we're trying to summarize the last few bits and pieces that are associated in this section. One of them is associated with strain energy. What do you remember about strain energy, by the way? Something to do with length.
Deformation over length.
Deformation, okay. Big picture though, conceptually. What?
Spring energy.
Spring energy, that's a great way of putting it. Anytime we're talking about materials, we're talking strain energy, think spring. Right? Whether it looks like a coil spring or not, if I take a big chunk of metal and I squeeze it, and I'm still in the elastic range and I let go, what's it want to do? Go back to its original size, which is like a big old spring. Okay? And if you keep that in mind, that makes this a whole lot easier when you talk about strain energy. So when you start putting the old classical work into it associated with that, how much work do you put into it, how much work do you got, or are you talking about potential energy and kinetic energy type thing? Same principle. I'm taking this big old thing, I'm compressing it, it's as if I'm putting a battery, putting energy into it, and then I'm letting the energy come out of the battery, it puts it back to its original spot. I'm just not using electricity, I'm using material properties based on the modulus of elasticity. So when I put all this together, I can use this to my advantage when I start talking about failure analysis and so forth. But the strain energy is kind of an important piece of information that allows me to put it in terms of the forces I'm putting on there and how much displacement I'm getting out of it. So those formulas, both for strain energy and the strain energy per unit volume, you're going to find in your cheat sheet, such that if you're given some concepts about the energy of something, or you know, sometimes I'll give you the strain energy itself. And you need to use this to reverse engineer to figure out what the force is based on the displacement they tell you, and then they'll ask you how much stress is in it. So then you go back to your force over unit area calculation. All right, so that's how those problems are going to be sort of formulated when they start talking about strain energy. These two right here are just a couple examples. You're not going to, these are not specific. The ones you need to remember about this, the basic one, they'll give you a formula if they want to go any further on the strain energy stuff. But that's all about knowing essentially how much energy the beam will store. So that's the other question would be, if I compress this spring, if I bend this beam, if I squish this thing, how much energy did I put into it? How much spring energy have I stored before I release it? It's kind of what they're driving at. And again, free body diagram is going to be your friend to start this off in order to do all the basic stuff about what the loads are, what the moments are, so you can figure out what the shear forces are in there. And then ultimately you go back and use the various strain formulas to figure it out. Now, this is an example. I think this is my slide. I put it on. No, yeah, I think this is it. See? Hang on a second. I'm trying to. I specifically wanted to point out a difference between them. But back to the strain energy problem, where I'm just using a typical beam bending like this. There's a formula for the transverse shear and the bending shear that are already given. You're just going to use those energy formulas, maybe not directly this way. They may be asking you a different question, which is, given the strain energy, what's the moment that's applied? And you just reverse the math as far as figuring that out. But those are the formulas you're going to use based off of the input values you were given in the problem overall. Let's see, compression. Oh yeah, oh, I totally forgot about this. You need to compress columns. Remember that stuff? No, that's why I'm in the class. I know, columns, you take a column, a big skinny column, you put a load on the top and the column's gonna buckle. Did you hear about the tallest building in the world was opening and people are moving in? Just, not Shanghai, it's Shanghai?
It's not Dubai anymore?
No, it's a brand new one, just opened. They just finished building it. Anyhow, what's interesting is when you go back and look at this stuff and remember it, there's a point at which a column will collapse under its own weight. It will buckle under its own weight. Now, I know the engineers, I'm sure, I hope, figured that out. But what I'm waiting for is for the tallest building in the world. It's the skinniest building in the world, skinniest, tallest building in the world. I'm waiting for the critical ratio, which I'll point out here in a slide, to be exceeded because the wind blew too hard or an earthquake came in or something they didn't quite plan for. That thing's coming down hard. And when you look at it, it's like, I'm not living up there. I'm an engineer. I'm not living up there. That's not doing it. But anyhow, columns can get compressed, and depending on how they're manufactured and what the different ends are, when I squeeze a column, put a load on a column in a building, they ultimately will reach a point, a critical point, where they will buckle on us and break. So I have a couple of different animals in the column world, whether they're long columns or short columns, and then things in between that have an off-center load. So they're going to ask you, very straightforward question will be, given a column of these dimensions and this particular axial load, what's the critical value of that column? And then you fill in the blanks with the stuff I'll show you in a second. The more complicated one becomes, given a column with an off-center load, much more rare. That question doesn't come up because it's a little harder to do, but it's still doable. You'll notice though, when I do an axial load, I get the benefit of the load being theoretically right down the center. When I put an off-center load, I get a moment, so I've created an additional moment. So it's not just an axial load, but it's also a bending load. Free body diagram again. Once you do that, you get the formula associated with bending and collapsing the column that way. But everything else associated with the column has to do with the ends and how they're fastened. Buckling. When the load reaches a critical load, that's when it buckles. That's not useful. There it is. That's what I was looking for. So we use Euler's formulas for these. The columns come in 4 different flavors. Those flavors depend on how the ends are fastened, because that dictates the response of the material to those particular loads. Now the overall formula, the P critical formula, is given down here. Now here's where I wanted to make some observations about differences, because this is a big difference between what you learned here and what you have on the cheat sheet. It's the exact same information. They just chose to use different variables, and here's where it gets a little confusing. So we did this formula right here for P critical, and we have this correction of this column factor, this constant that we use in here, C, times, in this particular case it's a round column, that's where the pi squared, the EI, and the overall length of the column come in. They don't use the value C, that big constant C, they use the value K. Funny, because they're both sounds, but in that case, you'll notice that constant is in the denominator down here. Everything else here in the formula is identical. So you'll notice we could write a formula or an equation that is the same of C and K to give you the same thing. Here's where it comes into play. When you're using Euler's basic formula right here, this is the basic formula, it's the same regardless of where you look. But because of these end conditions, I have a different modifier I put in here, that C or that K. And those end conditions are called fixed free, pin pin, fixed pinned, and fixed fixed. Let's see if that makes some sense. A fixed fixed. I've taken the column, I've put it in concrete, the next floor up is concrete, and I've sunk that column, it's all attached into the other floor. So now the ends of the column cannot move, and they can't even twist in the process. So in a fixed circumstance, like you see right here, those ends of the beam are not allowed to twist and bend it anywhere. They're kind of stuck at this exact point right here. Whereas a pinned, which is this first one right here, the end is allowed to rotate. In that case, I've got a floor in which I put a stanchion, a support stanchion of some sort, construction, or maybe I'm going to put a light on a rod of some sort. And I simply have a suction cup or something that's touching the floor, and I have another suction cup touching the ceiling. But fundamentally, those ends can rotate. There's nothing keeping the beam from twisting like this, meaning holding onto the beam and preventing it from twisting. So it can just pop out at any moment. That's pin. And then you have a couple of other combinations where you have a fixed pin. This one's sunk into the ground in the concrete, but this end is loose to go. And you have this one called pin free. I'm sorry, fixed free, thank you. Fixed free. This end is allowed to do whatever it wants. Imagine trying to take your finger and push on this anywhere it goes. All right? those end conditions with Euler's formula have already been figured out, and they've put together a little table with those values. So in the case of using the big C value, you can see it's quarter, 1, 2, or 4. So when I put it into the formula on the previous slide there, for any one of these conditions, I put 1, 2, 0, 4, a quarter in there, and my critical force will come out of that equation. You don't like C, but your formula is given as K. Here are the values for K, 2, 1.7, and 5. Mathematically, it's the same thing, because when you put those values into this formula down here and square it in the denominator, you get the same critical value. So all I'm trying to point out is, if you go back to your textbooks to do any of the review, you'll see the first formula. If you go and look at the cheat sheet for your exam, you're gonna see the second formula. It means the same thing. As long as you understand what the columns are doing, when you put load on them, you'll grab the right formula. Questions on that? That's probably the biggest deviation of anything I'm talking to you about today when it comes to your cheat sheet and what you learned in classes. There's a short example or a conclusion on the columns, just as a quick summary. Those are the two different versions of the equation up there. If you're looking for a couple other terms that might show up, this little k that's in here is called the radius gyration. The big K is an effective length factor, that's like our C. L is the unbraced column length. Now, that, to be clear, that's the usable length of the column, not the stuff that's in the ground that's sunk in there. It's just the usable part of the column that's between the two endpoints. You may hear something called the slenderness ratio talked about. All right? The slenderness ratio, depending on which one you look at, is either L over little k or big K over little k, depending on which formula it's in there. And the critical load can also be put together as a critical unit load, depending on how they ask the question. But the formula, right there. All you need to do is just quietly read the question and make sure you know which direction you're going, what answer you're looking for out of that formula. Okay? Yep.
Is there any other formulas we have to use other than this, or we?
I'll show you.
Okay.
When we look at the when we look at the summary sheet here in a second. Come on, Professor Collins made you sit the entire time, I bet.
Yeah.
Yeah?
That was right.
Yeah, he gave you one break, right? One break. That's all you got. He's good though. All right, Mike, Professor Collins. Okay, sit down. Why are you standing up so long? Oh! No cheat sheet. Let's look at it. Because this will make more sense now that we've got this thing up and running. There it is. Okay, so this is what you're given, folks, to get that exam done. And let's see if this makes sense to us. There's 3 pages, I can't remember, 4 pages long, something like that. Let's take a look at what's on here. It starts off, there's a little bit of uniaxial stress, and there's the stress strain curve for mild steel. Oh, we talked about the 2% offset. You know all about that. There's some definitions. What strain is, the length, engineering strain, percent elongation, so you can figure out the change in something. So you can notice, just be clear, the differential, the change over the original. So they may ask you the percent elongation of the material. There's the percent reduction of the material, or reduction in area. Shear stress, shear strain. Oh, not only did we talk about that modulus elasticity from the first graph, but there's that modulus of rigidity, or the shear modulus here. Poisson's ratio sneaks in, and that's how you can relate these two together. Given one, you can find the other. On the other side over here, there's the uniaxial loading deformation equations. So there's the force per unit area. I've been using F all this time. They're using P. Right? Same stuff. Longitudinal deformation, that little delta that's there. And that's all stuff we just talked about. Thermal deformation. Does it get warm? Yes. There's delta T times their length times the coefficient of expansion. Maybe they'll give you that. Cylindrical pressure vessels. We talked about those. And guess what? There's the formulas. That top one right there, internal pressure only, the stresses inside the wall are given this. External pressure only, the stresses are given by this. You'll notice it's the same formula, but they've got a separate one for you, and the radial stress is the external pressure instead of the internal pressure. All right? Don't be fooled by that one. It's pretty straightforward. They're just, it's the same problem, they're just pressures on the other side. Then there are all the different stresses defined for that formula. If you cap it, there's the new formula based off the radii. And if it's a thin wall, 1/10 of the radius of the diameter, there's your simplified formulas based off of thickness, the T that's in there. Principal stress, principal strain. There's the big uglies I was showing you. There's the 2 dimensions right there, the two principal stresses formula that we showed you earlier. They talk about the conventions where you arrange them 1 through 3 from algebraically largest to smallest. There's the unit stress cell or unit stress, keeps blowing my mind.
So definitely no 3-dimensional.
You better know the 3 dimension because it's coming up here in 1 second. Moore's circle talks about how you do it broadly. They give you an example of a Moore's circle and the math to do the Moore's circle right there as far as the where the center is. But again, if you just do the simple drawing like we did on that other slide, you've got it nailed. And all your answers are on that drawing. There's tau max based off of your maximum and minimum normal stress, the principal stresses. But you got to figure these out before you can figure that out. 3-dimensional, Hooke's law, there it is. And I didn't talk about it, but there's the matrix that goes along with it in order to do the calculations for the 3 stresses in the 3 different directions. Just remember that they get labeled in those multi-labeled directions. Don't let that confuse you when the problem gets presented. Most of the time they give you diagrams, so it's not that hard to recognize. And there's the strain formula based off of any of the forces and the torsions that are on. Torsion, speaking of that, there's the torsion formula right there. Torsion in a circular solid or thick wall. Notice that's greater than 1/10 of the radius. So there's the polar moment of inertia that comes up. Those formulas are on a different cheat sheet. You don't have them on this one, but you need them. Torsional strain. There's the hollow thin walled shaft formula we talked about. Bam, right there. Then there's a section on beams and beam bending. So beams, oh my gosh, when you're smiling, it's positive. Come on, lighten up. Stuff shirts. Positive shear, negative shear. Over on the far right hand side, these are some of the formulas associated with shears and moments and the differentials, stresses and the beams. We've already showed you this formula a couple of times based on the moments and the position and the modulus, or the moment of inertia. Distance from the neutral axis. There's that C, distance from the neutral axis, in that formula right there. So this is setting up a T, for example. That these formulas right here are setting up bending with a T or an I-beam. Now there's the transverse shear flow right there. You go right. There's the deflection of the beam. You see the first, second, and third, or second, third, and fourth derivatives. There's the shear force, and there's the ultimately the angular displacement. If you have a composite section, so instead of just a regular T, here are the formulas where you have that little factor N sneaking in there, which is the modular ratio. Okay? They may not tell you N, they will simply say that it's 2 materials. You need to go find this value by getting those from the tables. And there's the example of those 2 being done right there. And over here, columns, Euler's formula. Remember, theirs doesn't have a big C, theirs has a big K, and it's in the denominator. As a result, they give you K values. Piece of cake, we all understand it because we know the formulas are identical to the other formulas we learned. So we can figure out the critical force or critical load right here, which is primarily the question that will be asked, but they may ask you what the buckling stress is in the column. That's what's down here. You'll notice it's P critical over A. That makes total sense. Strain energy, there's the strain energy formula and strain energy formula per unit volume. Enough formulas yet? You were concerned about formulas. They're right there. And then finally, they give you a couple of tables. Check out the tables. It's good to know these are here. They give you the material. There's the modulus, modulus rigidity, there's the G's, Poisson's ratio, coefficient of thermal expansion, and the densities. anything you're gonna need in this section, all on that table, ready to roll. They also have a table full of yield strength, ultimate strength, because in some circumstances, they'll be using this context as the forces that are on the material. Alright, so that's why they give you another set of tables on there. But you'll notice Poisson's ratio, percent elongation at 2-inch specimen. If you use that, be careful. It's 2-inch specimen, not a 1-inch specimen. And then finally, oh my gosh! Those are the formulas for different loading. Whether it's a point load in the center, point load off center, a moment, a distributed load, partially distributed load, a increasing or linear distributed load, and deflection of not a simple supported beam, but a one-end fixed beam, a catenary or cantilever beam, cantilever beam, and there's even a pipe on there if you want it. But look, what's really important is what's over on the far side. There's the slope, deflection, and ultimately what they call the elastic curve. Go away. There's the deflection formulas right there. If you know the deflection formulas and you need to work up, just need to integrate them. If they give you a different formula, you can simply differentiate them, go down. Work your way through it, but there's the prime formulas already figured out for you. These are for the slope of the line. These are the physical displacement as far as the position, and these are the elastic curves. These are those polynomials that you saw we had earlier in the other formulas. That's where they came from. They've already put them in the table for you. And that right there is your cheat sheet. What does that mean? That means you can do this. Posted on a website is a practice, it's not the exam, that it has harder problems on it for you to fiddle around with just to kind of get a cobwebs out, and a mini practice exam. It's got 14 questions on it. Time yourself. I gave you 60 minutes, which is a little surplus, but you need to be able to whip through that in less that time. About 3 minutes a piece, should be about 45 minutes, right? Oh, is this where Van Steppen passes the Mercedes? Yes! And he takes the checkered flag. Oh my gosh. Get your butts out of here.
That was thrilling.